this. Yeah, hello everyone. So thanks, Eduardo, for inviting me. So basically, I'm going to talk about today, about the somewhat unusual use of this machine learning tool, which is TensorFlow. And so basically, these slides will be based on my talk I've given recently at the IML meeting here at CERN as well. But so maybe there will be just more technical details and some new benchmarks and newly discovered issues. So there's still a couple of questions to the way we use this tool. So just to introduce the problem. So basically, in LHCb, many of our analyses are actually amplitude analysis, and this is a rather powerful tool in, for instance, spectroscopy or CP violation studies and so on. So, so in this kind of analysis, you have to fit in a multi-dimensional kinematic phase space of your multi-body decay. Typically, we use like 3-body, 4-body decays. And the fitting function is some complicated function which contains dynamical kinematic terms, which is basically the interference of various intermediate resonances. So as a typical example, this is our famous pentaquark discovery analysis, where we are fitting the phase space of J psi proton kaon decay, lambda b to go into J psi proton kaon. And this is actually a 6-dimensional phase space if you count the two invariant masses and then the angular distributions. And just to give an idea, so there are a few tens of thousands of events, and we're doing the ambient maximum likelihood fit to rather complicated functions containing a lot of resonances. And this is where we find this pentaquark peak in the J psi proton invariant mass. So so what kind of math we are dealing with here? So this is shown in this slide. So well, obviously you don't have to understand this immediately. What's in there? So basically, the idea is that we have a decay density which is a combination of coherent and incoherent sums over different amplitudes, which contain some angular terms which describe basically the spin structure of this amplitude, and the dynamical terms which are somehow corrected Bright-Wigner's with some correction factors like what is called Blood-Weiss factors and the dependence of the width on mass. So this is what we're dealing with, and this is a so-called helicity formalism. There is an alternative approach which is so-called covariant tensors, which is more expensive computationally, but in principle it should give in the end more or less the same functions. So how we're dealing with this kind of fits. So of course you don't want to do this all this mathematics from scratch, probably, although some of the analysis do. So we actually have a few analysis frameworks to deal with all this mathematics, and here I show some of them, probably not the complete list. So the problem with all those frameworks is that they are quite not very flexible, I would say, right? So for instance, things like I mean, there's a package called LoRa++, which is a rather powerful tool for traditional two-dimensional Dulles plot fits. So this is basically a spin-zero particle decaying into 3 other spin-zero particles, which can do also time-dependent fits, and so on. This is in principle single-threaded, but there are many clever optimizations which make this code quite efficient. But when you want to extend it somehow to include something that is not designed for to be used with this code, for instance, the case of non-spin zero particles or four-body decays, then it becomes very difficult to actually modify it. So there is a Mint, which can do 3-body as well as 4-body final states. There's, I guess everyone knows here, GoFit, which is GPU-based fitter, which is also able to do amplitude fits. There's Ipanema, which is also GPU-based, but uses a Python interface, which I'm not very familiar with. But I think it's also used in a couple of analyses at OHCV. There's a nice tool called QFT++, which is not a fitter itself, but it's a tool to operate with, easily with covariant tensors. So in principle, you can write a fitter based on it. And there's still a lot of private code in use. And for instance, well, as far as I understand, all the baryonic decays, for instance, still use a private code for the fits, including the pentaquark analysis. So, so as I said, the problem with the existing frameworks is that they're not really flexible if you're trying to do something that is not actually foreseen in the design from the very beginning. I mean, you may want to implement something on your own, but of course you want this to be still efficient from the computational point of view. For instance, you want to do the fits fast enough so you can benefit from I don't know, GPUs, multi-threaded CPUs, and so on. But also you shouldn't forget about the trade-off between the actual person hours needed to implement the code and the CPU hours to do the actual fit. So there has to be some balance here. And I guess this is where the artificial intelligence tools come to help. And so we know that there is a lot of money now going into the good machine learning tools. So as far as I know, the Google budget for like development I mean, for scientific development is probably comparable to the whole CERN budget, something like this. And so basically the machine learning tasks and the tasks which are needed for the tasks of amplitude analysis, for instance, or any other complicated fits in high energy physics are basically the same. So you have to deal with large amounts of data. For instance, we are dealing from thousands events in like BDKs to millions or maybe many hundreds of millions events in charm samples. So we have to be able to describe complex models to fit to this data, which depend on some optimizable parameters like weights and biases for neural networks, or the amplitudes and masses and widths for our amplitudes. So we optimize by minimizing some function, which is called the cost function for machine learning, and negative log likelihood, for in our analysis. And we obviously need the tools which would allow us to conveniently describe those models and also perform the efficient computations. So this TensorFlow is actually one of the tools that I guess could be used for such tasks. So TensorFlow is an open source software library for efficient calculations that is released by Google like 2 years ago. So the feature of this library is that it uses a so-called declarative programming style. So instead of actually running calculations one by one, you first describe what you want to calculate. So you describe, as they call it, computational graph. And then TensorFlow inside it can deal with this computational graph to compile the code for some specific calculation backend, and while dealing with it, it can do some optimizations. For instance, it can identify which data should be cached, if just to avoid some common calculation repeating multiple times. Or it can compile for various architectures like multi-core, multi-threaded CPU, GPUs, clusters, and so on. And what helps us a lot, for instance, is it can also do analytic derivatives of your function to speed up the gradient descent. And since we are dealing with the gradient descent in MinWi as well, this can help a lot. So it has different front ends, and here in our case we're using Python, which is more developed and I think more convenient. Right. So just a brief introduction of the basic structures that TensorFlow operates with. So TensorFlow represents the calculations in the form of directional data flow graph. So you have nodes which are operations and the edges that describes how the data flows, right? So for instance, if you have a function that describes a sine wave, right? So this is the amplitude and the sine of the frequency times whatever, time plus some phase, right? So it will be described by the graph like this. So you have the input structures, which are phase, frequency, and your data, right? So you multiply this, add this, this goes to calculation of the sine, and then you multiply it by the amplitude, and this is the result of your calculation. So, in TensorFlow, most of those operations like this, sine, multiplies, and things like that, they're vectorized, like in NumPy, for instance. So, for instance, if you write TF sine of x, it will calculate, and x is some big tensor, it will calculate this sine element wise for each element of this tensor. So this is quite useful, obviously, for maximum likelihood quiz, because you typically need to calculate the same function for each point on a large data set, be it the data or normalization sample. So those input structures here are, there are two kinds of input structures in TensorFlow. So first, these are placeholders, which are some abstract things that are assigned a value only at the execution time, and typically this is in machine learning, this is your training sample, or in our case, it's the data sample you want to fit. And then you have variables which are assigned some initial value, and this value can change over time while the minimization is done. So these are typically the tunable parameters of the model. Right. So just an example of how the fitting script could look like in TensorFlow. So at this point, I'm just speaking about TensorFlow and not about any kind of physics analysis that we're doing, right? So this is pure TensorFlow stuff. So you first need to build the graph for your calculation, and you define your inputs in the following fashion, right? So you have x, which is going to be your input data tensor, which in this case it's just a one-dimensional tensor of the unknown size. This none tells you that you don't know how large the data sample is. Then here are your tunable parameters, and this is your definition of the graph, right? So it's quite trivially written. So at this point, there is nothing is calculated, right? So it's just you're just describing what has to be done. So now, when you start to execute things is when you create a TensorFlow session like this. So it initializes the variables, and then inside this session.run, you actually do the calculation. So when you write session.run, TensorFlow will compile this graph, and then
using this feed dictionary, you are feeding your data into this graph, and as a result, you get the output. So you're feeding 4 values, you get the output, which is also 4 values, for instance. So the input and the output are, for the session run, are just commonly used NumPy arrays. So TensorFlow has its own minimization functions, which are good for typically for of course for machine learning, but maybe not very well suited for physics. So just an example here. So well, for instance, you have some chi-square measure you want to minimize, and some data you want to fit to, right? So now you're feeding the input data and the output, and you're minimizing the chi-squared, and you define your gradient descent optimizer like this, which will minimize this chi-squared, and this loop will run 1,000 steps of gradient descent. Like 1,000 times it will run this optimizer, which is gradient descent optimizer. Well, in physics we don't do just gradient descent, right? So we need to make sure that we know the uncertainties. We should be able to do likelihood scans, and we should be able to tell whether we have found a global minimum or a local minimum, things like that. So this is something that the TensorFlow built-in optimizers cannot deal with, as far as I know. And this is why in our package we're actually using Minui in just the PyRoot interface for Minui. And while the function that has to be minimized is actually calculated inside TensorFlow. Right. So there are some useful features which are quite convenient for the amplitude analysis in this library. As I said, it can do analytic gradient, which is extremely useful. So you will see the benchmarks in some time. So it can automatically calculate the gradient of your likelihood function, and this can speed up the convergence of the fit quite a lot. And well, fortunately, Minui can actually use this analytically calculated gradient in order to run minimization. And in TensorFlow, this is done automatically and in a very simple way, right? So you have some tree, and for chi-squared, for instance, and this line basically tells you calculate the gradient of this function chi-squared with respect to some number of optimizable parameters. That's it. There is, in theory, there is something that is called a partial execution in TensorFlow. So in principle, TensorFlow should be able to identify which parts of the graph need to be recalculated. For instance, if you're changing the value of some of the variables while others still stay the same, it should be able to identify which has to be recalculated and which you can take from cache. So in practice, this doesn't always work as I would expect. But there is, in principle, a possibility to do this manually and to tell that, well, some parts of the graph actually needs to be calculated only once at the start of the minimization, like, for instance, the helicity factors in the amplitudes, which usually don't change as a function of the amplitudes or masses or the widths that you are fitting to. But in TensorFlow, there's a possibility to inject some value of a tensor manually, and this can also improve the time of the calculation quite significantly. So finally, a useful feature that allows us to avoid basically rewriting from scratch some of the mathematical functions that are not there in TensorFlow is the interface with SymPy. So, well, obviously, people doing machine learning, they don't care about I don't know, spinors, Wigner-D functions, and things like that. So TensorFlow has an interface with the SymPy. SymPy is a symbolic algebra system for Python, so it could consider as a Mathematica with the Python interface. And in particular, it has extensions for physics calculations. For instance, if you want to define a Wigner-D function, which basically describes the projection of the spin projection in some angular observables, in principle, it's just a complicated complicated function of sines and cosines of some angle, depending on the spin and spin projections of the particle. So in this case, you don't need to write it from scratch. You can just call something that's called lambdify, which is a SymPy function, which will generate the TensorFlow tree for something that SymPy already knows. And for instance, this Wigner-D already knows. Right. So finally, we have a package that is called TensorFlow analysis, and you will see the link to the GitLab here in this slide. So basically, what we want to do for amplitude analysis is basically have a root interface to read-write our antiples with the data. So you could use root numpy, or there are some simpler functions in this package. There is a MinUI interface for minimization, and just a library of various HEP-related functions which you could use as the bricks to build your amplitudes. And then TensorFlow actually serves as a framework for fitting itself. So in principle, even without any kind of higher-level package, you can write a standalone Dulles plot generation fitting script using just TensorFlow and root in just like 100, 200 lines of Python code. So the Python code is actually quite compact. And for instance, I mean, calculating relativistic bright Wigner is just one line. This is the unbinned log likelihood, where basically summing the logs of the PDF and normalizing to some this function using some Monte Carlo integration sample. Right. But so this package just provides a collection of standalone functions, as I said, for the components of the amplitude. So what we have, what kind of functions we have is, first of all, the phase space classes, where we are doing the fit. For instance, the two-dimensional Dulles plot, which is some complicated, more or less two-dimensional shape, depending on the masses of the initial and final state particles. The phase space for four-body, which is five-dimensional, baryonic three-body decays, which also includes angular observables and so on. So these classes provide functions to check if your set of your kinematic variables is inside or outside of this phase space, to generate uniform distributions and so on. Then there's a fit parameter class which adds some useful features for MinUI to the TensorFlow variable. So for instance, MinUI wants range, step size, and so on. Then there is an interface to MinUI itself, where you want to calculate the integrals of your function, the unbinned log likelihood, and so on, and to call MinUI itself. There are functions to run toy Monte Carlo generation, to calculate fit fractions for individual components, and so on. And there's a large collection of functions for amplitude description, like Lorentz algebra, kinematics, helicity amplitudes, Zemek tensors, dynamics, which is various line shapes like Bright-Wigner, Flatte, whatever have you. There are elements of covariant formalism as well, like polarization tensors, gamma matrices, and so on. And if you want to deal with real data, you need to be able to describe your backgrounds and efficiency shapes as some more or less non-parametric shapes. And the point is that you have to use this. You have to actually describe them in terms of TensorFlow tree as well. So there is a class for multilinear interpolation of root histograms. Right. So the fitting script is presented in the next couple of slides. So first of all, the experimental data are presented as a two-dimensional tensor where you have the inner index, which is your event or candidate, and the outer index is the phase space variable. For instance, if you have Dalitz plot, which is two-dimensional, you have this is just 2 dimensions. For four-body case, it's 5, right? So on. So in your fitted script, you start from the definition of the phase space, which, for instance, you have the Dalitz plot phase space, which is a function of masses of the initial and final state particles. Then you describe your fit parameters. So this fit parameter is again, as I said, the class which extends TensorFlow variable. And now you're describing the model as a function of the phase space variable x. Right? So this phase space has the methods to access whatever invariant mass, for instance, combinations. Then you describe your amplitude as a combination of Bright-Wigners and angular observables, and then you return the absolute value squared of the amplitude. And this is your fitting model. So there's one technicality that so you have to normalize this function, right? So you have to have your data sample and some normalization sample, whatever the rectangular sample or the uniformly distributed Monte Carlo, or maybe not uniformly distributed Monte Carlo, and your likelihood typically has this kind of form, right? So your data sample and normalization sample enter differently. So you have to create actually 2 graphs for the data model and the normalization model, and then combine them in the calculation of the negative log likelihood. So the integration and negative log likelihood are again provided in this library, and then you call run minui, where the parameters are the session you have created, the TensorFlow session, your graph for the negative log likelihood, and here you are feeding your data sample and normalization sample. Right. So internally, this call already includes all this fancy optimization, like analytical gradients and so on. So what's the good thing is that you have a full control over, how this likelihood is built, right? So you can consider, for instance, like fitting multiple Dalitz plots for, I don't know, if you're studying CP evaluation, you want to fit B pluses and B minuses and so on. So you can basically deal with this quite conveniently. So for instance, if you have a combination of 2 Dalitz plots, you can just write the negative log likelihood as a function of the 2. And similarly, if you have some complex combinations of the fit parameters, it's again quite easy to deal with this. So there is an example, for instance, of this CP evaluation enabled toy Monte Carlo for psi b to pkk, which is one of the analyses at LHCb that is dealing with this TensorFlow analysis So it's using this package to actually do the fits. Right. So a couple of examples. So we unfortunately don't have any analyses that are published. There are several of them who are approaching publication, but none of them is published. So these are just toy Monte Carlos, right? So this is an example of the traditional Dulles plot, D0 to K short pi pi. This is the baryonic decay lambda b to dp pi, where the blue points are the generated sample, toy generation, and the red ones, the red line is the result of the fit. So there are some examples in this link here. What are the plans and issues so far? So there are still some areas where we have to do some development, and for instance, we need to extend the library of functions as needed by the analysts. For instance, we don't have any K-matrix implementation yet. We can also consider some more fancy analytical coupled channel approaches that are appearing. So in principle, could be interesting to have saving loading of the compiled graphs, because when you're running, for instance, a lot of toys, it's quite, every time you run your toy, the TensorFlow internally has to compile the graph, which takes not a lot of time, but still it could be better to actually just load the one that is already compiled. Then we have to obviously identify what kind of possible optimizations for CPU and memory usage could be. Maybe use more symbolic maths. Right. Just skip this. What I find quite useful is TensorFlow has an internal profiling possibility that you can quite easily turn on profiling, which will produce some JSON file, which after you load it into your browser will produce pictures like this. So for instance, this is how for 32 core Xeon, the operations are broken up in various cores. And so in principle, using this kind of pictures, you should be able to identify the possible bottlenecks in the execution speed. So X is time, Y is the core number, the core number. So just some benchmarks here. I've tried to run it on a few machines. Here, CPU1, GPU1 is basically a not very powerful desktop machine with a gaming card. CPU2, GPU2 is a more high-end machine we have in Warwick. Still, this GPU2 card is something that is not designed to work with double precision. And then recently I was able to run this test on the same machine, but with the K20 card, which is already it's quite an old but rather decent card capable of doing double precision. So the results are well, first of all, in terms of the use of this analytical gradient, you can clearly see the gain, right? So well, in some cases you get a reduction of like more than 10 times in the number of iterations you have to do. So this clearly helps a lot. What's disappointing is that actually it is this package in its current form is unable to use the full power of the high-end GPUs. Right. For instance, you can see here how the CPU versus GPU is different, and it's clearly is not able to use all this power of multiple teraflops for this Kepler card. And I guess the problem is probably that. Okay, I'll talk about it later. But
just one quick question, just
yes.
for that.
Yeah.
So for the K-short pi, is that just a time integrated analysis, no time dependence?
Yes, it's just a two-dimensional fit. Yes.
So my immediate reaction is that seems really truly slow compared to other packages that are available today.
Right. So that's
just you know.
That's true.
Have you compared this with any of the other packages that you described earlier?
Yeah, I think Henry has some comparison with Goofy, obviously. But the point is, I mean, this technique is definitely not. I mean, it cannot compete with Goofy for whatever Goofy is designed for, right? So the power here is that, I mean, it's quite easy to describe arbitrary amplitudes, like, I don't know, periodic stuff and so on.
But last summer for the lambda c goes to 3-body decays.
Yes.
And I think you're absolutely right that TensorFlow, because of the libraries that are already existing for things like the Wigner D matrices, the interface is very human friendly.
Right.
But it was a really, really slow fit.
Yeah. So here I have a list of some problems that I am facing with it, right? So and possible explanations and ways to deal with it. So as far as I can see is that, well, so you can see that this high-end GPU and basically the gaming GPU is more or less the same numbers, right? Which just doesn't make sense. So it is not able to actually utilize all this GPU power, and I think the problem is probably either the memory latency or the bandwidth of.
Probably the memory. Based on what we've seen with Goofy, it's probably memory latency.
Right.
And
so
I think you're going to find that for almost any of the problems that we're doing, that you're going to run into something like that. So
right.
I don't think we should ever expect to see phenomenal GPU processing power.
Right. And so actually, well, looking at various forums on the internet, I find that, well, actually many people complain about this stuff. So
when you move to the next generation, when you go from the K20 and K40 are part of the same generation. The next generation is the V100. Not the V100, the P100.
P100, yes.
P100.
So I didn't have a chance to try it, but I think they have it at CERN in
so a P100 is about 3 times as fast as a K40 on the same code base.
Right.
So, and I think that's because they have lower latency in memory.
So I think that the real problem with TensorFlow is that it cannot do the so-called kernel fusion as you can do in Goofy, for instance, right? So typically people recommend to to compile the kernel that takes some data from memory, that processes on the GPU core, and then puts that back, right? And so that to minimize the number of read and write operations into the video memory. So just to utilize the cache as much as possible.
And you're going to go through all of these details. Maybe you want to finalize it, right? And then
right.
Because otherwise,
no. I mean,
discussions.
Right. So and well, in principle, there are some possibilities that I've just discovered quite recently. For instance, this just-in-time compilation option that you can enable in TensorFlow if you build it from source. So this could potentially probably help with this memory latency problem. But I mean, we just need to try and see. Right. So well, as I said. So here are some problems, right? So first of all, at CERN you have to deal. I mean, you just cannot run it on a typical LX Plus machine, right? So you have to use this CentOS because it needs a rather fresh basically libc library. So there are problems with memory usage. So with like consumer cards, you can easily exceed a few gigabytes of RAM. So it should prevent you from running large data sets like Charm. But I guess with like multiple, if you have a few tens of gigabytes, that should be pretty much enough. So double precision is definitely essential. So I tried to run single precision fits, but it just doesn't converge. So you need to run double precision. So as I said, performance issues with high-end GPUs, and this is something that we have to investigate. So far, in all the analysis that we are running, we are running on the CPU, and so I just started to play with high-end GPUs, and I guess we can improve things somehow here. Something I've discovered is that the results are actually not reproducible sometimes between different GPUs and CPUs, and I guess this is because the implementation, the implementation of the floating point is everywhere slightly different, so you cannot sometimes literally reproduce the same results if you're going from between different GPUs. And some people even complain that TensorFlow is sometimes it doesn't reproduce itself if you run multiple times on the same machine.
Oh, but that can also be part of Minway, because there are places where you make random choices, and if your random number generates starting at a different point,
yeah, but I think
you don't have to converge to exactly precisely the same place.
No. So well, people are telling that well, some of the neural network training is actually, sometimes you can just, if even starting with the same seed, you sometimes get different results because of the way something in the lower level libraries is implemented. I haven't seen this with our fits, but I cannot guarantee that this doesn't happen. So right, and as I said, this is definitely less efficient than the dedicated code with GoofIt or whatever, but I think it's way much more flexible and easy to program. So here are some examples of what kind of fits you can do. I probably won't go into details here, and just my summary. So I think this approach is quite promising, although of course there are still some issues with this, right? So you can utilize, at least in theory, modern architectures. You can compile the code for whatever multi-threaded GPU backend. There are some interesting optimization options. For instance, this analytic derivative is, as far as I understand, this is the unique feature, and I'm not sure if anyone has ever implemented in any other amplitude analysis frameworks. The code structure is quite transparent, so you don't need to go like low level to write your amplitudes, and the models are very portable, and I think with some minor effort we can even make them is like a universal tool to describe the amplitudes, and maybe to give the some code for the theorists to reproduce and so on. And of course, this is a very useful training value for the students who will eventually leave high energy physics for industry, because the TensorFlow is becoming really an industry standard in many areas. Yeah, so we have this TensorFlow analysis package, which is basically a collection of functions, and this is still in rather active development, and it's now used in some analysis at LHD, but none of them is published yet. Right, so that's it. Thanks.
Well, thanks very much, Anton. Maybe questions from outside, since we already had a few discussions from here from CERN.
Hi, I have a question. Here. So, my main question is, so in the examples that you gave, where using Minway you do the fits and you get a number with it, does this also return a statistical uncertainty for the central values that you obtain? I missed that point, maybe.
Right. Yes. So it's completely using MinWe. So whatever MinWe can provide, you can get as well. But inside it just uses TensorFlow to calculate this whatever called FCN in MinWe, right? So yes, it does.
And if I could just ask another small question regarding reproducibility of the results. Like, do you have handles to the various random number choices so that if you wanted, you could reproduce the same result on the same machine?
Yes. So I mean, you definitely have a way to set the random seed. The point is that, I mean, if you're running the same script literally with the same random seed on, for instance, on a CPU and on a GPU, you sometimes get different results.
When you say different results, can you quantify how different?
Well,
is it somewhere around the 17th?
No. So they're, obviously they are somewhere in the seventh digit of the floating point. But I mean, you cannot reproduce literally. I mean, for instance, the number of iterations can be different, right?
Yep.
Which is not a big deal for your paper. For the benchmarking, it creates some problems because sometimes you have like different number of iterations, sometimes like a couple of times different. But yeah, I mean that's just I guess it's just it's a very minor point.
Okay. Thanks.
I think that's primarily a feature of MinWe.
But I'm not sure that MinWe is non-deterministic. I mean,
if you were to start with exactly the same thing everywhere on the same machine, it should be.
Yes.
But
I mean,
if you start with very slightly different initial parameters,
yeah, of course.
The point where converge is I don't know where it is today, but it was traditionally means 30 or 40 years ago. You were guaranteed to be within 1/10 of its reported sigma. It might be down to 1% of its reported sigma. But there's still some uncertainty out in the extra digits, and no one should ever believe it's better than that.
I'm pretty sure that's true today for MinWe.
I haven't benchmarked it recently. In my youth, I was more creative about testing things.
Any more questions or suggestions? Or I have one. For example, you said at some point that you extended the variable. Have you thought about actually trying to contribute to TensorFlow itself, adding an enhanced variable, just to see how they are open to the different community?
No, I haven't tried.
Actually, it could be interesting just to flag them that this is used in a completely different domain, right? It could be see how it goes, basically.
Yeah, I mean,
we'll talk about the whole package, but there's probably a few concepts that could be ported there. Okay.
Yeah, I mean, this has to be coherent with. Maybe at some point it will make sense to actually have MinWe interface built in TensorFlow itself, right? So there's a version of MinWe which doesn't depend on root, for instance, and I think it could be also useful for people. I don't know about the licensing issues.
Yeah.
Yeah. But I mean, all the built-in minimizers, they just they are designed to provide some optimum, right? So when you're training your neural nets, you basically you're just trying to approach to a certain minimum. I mean, there's no way with millions of parameters to make sure that you've reached the global minimum. Typically, the neural network should behave well enough. And from this point of view, the tasks are a bit different.
But MinWe, and actually any numerical minimizer can't guarantee that you find a global minimum either. In fact, if you're really if you're really adamant about global minima, you need some sort of metropolis. You need a simulated annealing, which I think Minuit is not.
No, yeah, but I mean, still, there are, some techniques that it applies to actually at least try to to make sure that this is not just a local minimum, right?
So I've been reading a lot of machine learning recently. If you have 36 free parameters, the likelihood that you ever encounter a local minimum is almost vanishingly small. You're much more likely to hit a saddle point.
Yeah.
So if you're at an extremum, right, where you have a local gradient, and you're to the n, and you have to hit all n as a minimum, you're actually probably not. Minuit was designed to do a local minimum, and it's not clear that it was designed to address the issues of saddle points in multidimensional spaces very well. There's lots of evidence that it fails.
Yeah.
Mm-hmm.
But you're right. The machine learning typically uses the back propagation. That's what the TensorFlow design is meant to optimize. And that's a completely different approach to minimization.
Yeah, I think they're designed to deal with very large numbers of free parameters.
Very large numbers of free parameters and nominally linear-ish relationships.
Yes.
But I don't think this is a special built-in TensorFlow. I mean, what you're talking about stochastic gradient descent essentially, but I think in TensorFlow you can just do computations in general and you can get the gradient. So now Minuit just does a line search essentially, I think, and I think also Minuit supports the analytic gradient if you have it. At least Minuit 2 does.
Yeah, that's what he's using.
Yeah, this is what we're using exactly.
Yeah,
yes.
I think what he's saying is that the nice thing about the TensorFlow framework is that people have provided libraries which do the analytic differentiation for you and therefore provide the gradients where most users of Minuit, you can sit there and you can use all the derivatives by hand and plug them in, or if you're a little bit better than I am, you can go and take your original functional form and give it to Mathematica and let it calculate the derivatives, and then you write your code that way, Minuit, and you can try to get the same sorts of speed ups that Anton's described. I know Pierre Raven has done stuff like that with his use of Minuit. And he also gets very large speed ups, of similar magnitude. The nice thing about this package is that it lets you do that type of work
absolutely
almost transparently. The Python packages are there. Someone's written those Python packages and you can use them. And it's really easy to write I started with Anton's stuff from the lambdas of CDK. I don't see it described here, but it doesn't matter. It's 3 by k. And with some undergraduates, we modified it to do lambda COs to PK pi, P pi pi, PKK, almost trivially adding bunches of resonance that we found in PDG. The fits themselves, which let masses and widths float, were a bit slow, even on a P100, 40 minutes to do one fit, which I thought was pretty dismal. But the human effort was really excellent.
Yeah, that's what I'm about. So, I mean, there has to be a balance between.
I would love to see the same effort you're making here for TensorFlow put into GoofIt, so we can do everything as smoothly as you're doing it here and with the speed that we have. I think it's possible.
Yeah. So my nearest plan is actually try this JIT thing, which well, in principle, is promised to actually get rid of. I mean, well, not get rid of, but at least minimize the effect of this memory latency on the calculation. Because at the moment, as I understand, TensorFlow has like a number of already precompiled kernels, and for instance, I mean, so it takes something from memory, calculates sine or cosine, and then put it back into the memory. So it doesn't do this kernel fusion.
So there's one standard trick that everyone discovers, and you probably discovered this for doing analyses, that if you cache the products of the real and imaginary parts of the amplitudes at each point, and then just multiply by coefficients, there's typically a speed up of another factor of 10. I don't know if you're doing that. If you're not, you will discover that one day and say, oh, there's another factor of 10.
I know this trick. I'm not doing it here just basically because it removes the transparency of the amplitudes, right? So you have to.
Okay, so we can talk about this offline.
Right.
There's
an easy factor of 10 there, guaranteed.
Yes.
And I think TensorFlow has the caching stuff built in. It has the
So what I definitely do is I'm caching all the helicity tensors, for instance. For baryonic decays, it's a big deal typically.
Yeah.
Because although sometimes actually it becomes even worse, and I guess this is again, I mean this memory bandwidth or latency issue. Sorry.
Okay, this is.
Should we do a fun one?
We can talk about this offline.
Yeah.
Yeah.
I don't know if there's any more questions or comments. Otherwise, I think we
I did.
had a. Yeah, please.
I had a fairly technical point. The comment about LX+7 is, at least in CMS, we've gotten around that. I'm happy to share a recipe if you would like it for at least for CPUs.
Wait, could you say that again? You can use TensorFlow on Scientific Linux 6?
Yes.
Cool.
Interesting.
The answer is yes. Send it around.
Yeah, I guess you need to compile it yourself.
Yes. Yeah,
There's
that's right.
somewhere behind.
Yeah.
Okay. If nothing else, then thank you very much again, and see you at the next meeting then. Bye bye.
Yeah. Thanks. Bye.
Thanks, Anton.